Very good. So welcome to this new session of the Galileo Galilei workshop. And our first speaker of today is Radu Roiban, discussing particle physics methods for high order in the PN and PM expansion. So I will tell you 15 minutes before the end of your talk, please.
Great, thank you. Thank you very much for the invitation to speak here. So I was asked to speak about PN and PM methods. And since the results have already been announced in Zvi's talk a little bit during the conference, I figured that what I will talk about is actually some of the technical details that went into deriving those results. So the examples throughout the talk will be taken from work done with Zvi, Cliff Chung, Andres Luna, Julio Para-Martinez, Michelle Roof, Choishen Shen, Mikhail Solon, and Mao Zheng. And of course, I will not be talking about all the methods. Some of them will be covered extensively in Mao's talk tomorrow. So gravitational interactions, despite their long history, are still not terribly well understood, and we are still working on understanding them. There are many approaches to these, to the problem of understanding these interactions. Some of them are field theory based, some of them are string theory based, some of them are word line based, twistors, numerics, you name it, it's probably having some something to say about gravity. But each of these methods emphasize different aspects of and expose different aspects of gravitational interactions. It is said there is nothing like an explicit calculation. So this is actually something that is quite valuable, doing explicit calculations, because they tend to expose structures and patterns, which in turn could and sometimes do lead to new methods, which in turn lead to more calculations, and eventually they lead to progress. And this cycle actually repeated already a couple of times in the context of this workshop. Well, in the last few years in the context of this workshop. And in the context of particle physics, it repeated many, many times over the years. So it's a good picture to have in mind. So for the case of interactions of matter with gravity, the technique, which is the purpose of this discussion, the technical goal can be formulated in several ways. One of them is the calculation of a partition function or an effective action. And my pointer doesn't work. So the idea is we start with some matter, denoted here by some field phi, coupled with gravity, denoted here by h, and an action, which we assume that in some fundamental theory is a local action. And then the goal is to integrate out the off-shell parts of the gravitational field and perhaps the negative energy modes of the matter fields, and obtain an action gamma, which depends only on the pieces of the graviton that can escape to infinity and the positive energy modes of the matter. And this could eventually be used to understand classical interactions. So that would be one way to formulate the goal. Another way is to bypass this partition function story and attempt to construct, by whatever means, observables or generating functions of observables which capture the entire physics of that in the first version is captured by gamma, and then take it from there. So now, if one has gamma on one's hands, one could equally well treat open motion and motion on bounded orbits. The only difference is, for example, the only difference is changing the boundary conditions for the equations of motion. And because of this, one could attempt to find gamma not by directly integrating things out in this formal partition function kind of way, but from a scattering amplitude type calculation, from a scattering angle, for example. In the second kind of approach, one has two options. One could basically reduce this to problem one, that is, use the observables to find gamma, and then use that for whatever means one, for whatever purposes one desires, for example, discussing bounded motion. Alternatively, one could attempt to take directly the observables and analytically continue between open and bounded motion, as was formulated by Kalin and Porto not too long ago. For the purpose of either one of these two approaches, one has several methods. For example, one could use a first quantized or a wordline type approach where the starting action is a point particle action, Einstein-Hilbert, together with some gauge fixing. And I will not say anything more about this because the next talk will use this, this kind of approach, to my understanding. So the second version, which will be the purpose of this talk, is, or at least the focus of this talk, is a second quantized or four-dimensional quantum field theory type of approach, where the action, as I was mentioning, is some matter action coupled with Einstein-Hilbert and some gauge fixing. And we will quickly do away with the action. But as a to lay the groundwork, this is if one were to actually approach the calculation via partition function, this is the starting point. So in here, the emphasis is, of course, on the quantum, but one can take the classical limit early on. And also one also needs to separate the negative energy modes of the matter fields. So in both cases, the gravitons that are integrated out are identified via the so-called method of regions, which amounts to splitting the graviton momenta into several pieces, the so-called hard part, where the loop momenta, that's the graviton momenta, is of the order of the energy of the process, and then the soft ones, which are further split into potential and radiation. With in the former case, the loop momenta or the graviton momenta being of the order of the momentum transfer with an energy which is substantially different by a factor of the velocity. And radiation in which both the space-like and the time-like momenta, components of the graviton momenta, are of the same order, velocity times the momentum transfer. Clearly, the former are very far off shell, or at least far off shell, whereas the latter can, in principle, be on shell. So because of this, the former kind describe essentially instantaneous interaction because the energy is much smaller than the space-like part, whereas the latter could describe interaction that takes a fairly long time, and it does have energy transfer. So most of what I'm going to say will be in the context of integrating out gravitons with this kinds of momenta, and we will be aiming at constructing a potential. But the techniques that I will describe could equally well be used to integrate out gravitons of this type. So again, the goal is to review particle physics methods and describe the limit classical quantum to classical. And the emphasis will be on the construction of integrands that appear in this game, and the integration will be covered by in Mao's talk tomorrow. So, of course, the first question one can ask: why start with quantum and go to classical? And I'm sure this question has been asked many times, and everybody has their favorite answer to this question. My favorite answer is that the quantum framework is more constraining, and at the same time, it is not more complicated than the classical framework. Of course, the notion of complicated is in the eye of the beholder, but like I said, this is my picture. And there is, of course, an intuitive analogy to this, and that one relates to integrable models. In that case, in that framework, one's goal is to diagonalize a Hamiltonian. However, that turns out to be difficult, but it becomes quite tractable if one realizes that there are infinitely many Hamiltonians, and once one attempts to diagonalize all of them at the same time, then the problem becomes tractable and it's entirely algebraic. So these additional constraints provided by the quantum framework and Lorentz invariance are basically what is behind the idea of using the quantum framework for classical physics. So once one starts with a quantum framework, one needs to talk about classical limit. And again, this limit is, everybody has their own favorite way of taking it. Mine is in the context of the correspondence principle. You just take all charges to be large, and if you do that, all conserved charges to be large, and if you do that, then classical physics will fall on your lap. So to describe this in 30 seconds, the first thing that I'm going to do is to set h bar equals 1. And that will set our meter stick. So everything will be described in terms of physical quantities. So the classical limit is the one in which we scatter particles such that the de Broglie wavelength of each particle is substantially smaller than the separation of the two particles. In this regime, we never have to talk about quantum interactions between the two. So this limit, because the de Broglie wavelength is essentially 1 over the momentum of that particle in these units, and the separation is of the order of the inverse momentum transfer, just implies directly that the momentum of the incoming particle is much larger than the momentum that's being exchanged between the two particles. And in turn, this implies that the angular momentum, the orbital angular momentum, is much larger than 1, just as instructed by the correspondence principle. One can, of course, apply this also for spinning particles. So in that case, one, of course, since we're talking about classical physics, we need an object of finite size, call it R0. And then the de Broglie wavelength of that particle needs to be much smaller than this size R0. And then the intrinsic angular momentum, just straight out of this, ends up being much larger than 1. So this is our classical limit. And of course, I'm not saying, as far as the result is concerned, this limit is nothing new. This is what has always been said, and everybody agrees with this, I hope. I hope this picture is perhaps a little bit more intuitive than restoring h bars, for example, but not necessary. Now, the other thing that it's worth emphasizing is that this limit does not need to be taken at the very end of calculations. It can be taken as early on as one desires. And that's exactly what we're going to do to simplify our life, to simplify the calculation and our life. So there are two main particle physics-based approaches to gravitational interactions, to understanding classical gravitational interactions that have been on the market. One of them is to start with scattering amplitude and construct a Hamiltonian via matching with an effective field theory, which has this form. So the idea is one constructs amplitudes here and equates them with the amplitudes of matter plus gravity. And then from here, one extracts this V. Now, as it turns out, this V can have different meanings depending on the details of how this matching is done. And this is an important point. So as was, and that has to do really with the choice of two-body propagator here represented by this bubble. So in the original work of Chung, Rothstein, and Solon, they picked something that they referred to as Y-poles. That is, this two-body propagators looks like this. P is the incoming momentum. L is the, should have been K. L is the loop, the gravitational momentum. Sorry, the momentum in this loop, which is actually a matter loop. So with this kind of two-body propagator, V turns out to be a potential. And this object as a whole can be interpreted as a particle Hamiltonian. If, however, one picks a different two-body propagator, like this, then this V is no longer a potential, but it turns out to be the radial action. So to be more specific, this is the actual relation. The amplitude is, of course, because we're talking about an elastic process, it's an exponential. This is really the S matrix -1. And then this I has these expressions. And the point is really that this Z's at the bottom, which have this this expression. They are linear in the gravitational momenta. And with this definition, I turns out to be the radial action. And this can be actually checked directly in an effective field theory calculation. There is no need to match this the EFT with anything else to see this. Now, one might, of course, ask the question, gee, but there is only one amplitude. What are you doing here? Well, the idea is that the difference between these two choices of poles represents a different choice in in these i's here, and especially in the choice of what of iteration terms in the amplitude. And this is what leads to the difference in the interpretation of V potential versus radial action. Now, in the same spirit, starting from a scattering amplitude, one can, of course, construct an iconal phase. And this was described in Russo's talk at the conference, so let me not dwell on that. And the second particle physics-based approach is the one pioneered by Kashauer, maybe, and O'Connell. And that bypasses the construction of a Hamiltonian and goes straight from amplitudes to observables. The idea is, well, the procedure, or the, it's captured by this equation, which basically says that the expectation value of some observable in the final state is given by the expectation value of the corresponding operator commuted with the S matrix, and the matrix element is taken in the final state. And pictorially, it looks something like this, illustrated for the momentum transfer or the impulse. So there is a piece that comes from the first term, which is basically just the scattering amplitude times the momentum transfer. And then there is a piece that corresponds to intermediate states in here, which may be 0 gravitons, maybe 1 graviton, maybe 2 gravitons, and so on. And these gravitons can themselves be either potential or radiation. If one restricts to just a potential type of graviton, then this would give the contribution of the potential to this observable. If one includes also radiation type gravitons, then one obtains an actual, the complete observable. Now this is an amplitude-based approach. These are amplitude-based approaches. So Lorentz invariance is naturally built in. Of course, at any stage, one could choose to expand in velocity and obtain whatever order in the Pn expansion one desires. At the limitation, so to speak, is that if one wants to obtain complete orders in Pn expansion, then one needs various orders in G, in Newton's constant, in the various amplitude factors here, or in these momenta, or in these interactions. Right. So now that we know what we want to compute, that is amplitudes, let's see how we compute them. The strategy is the generalized unitarity and double copy. And this is at least the first part. Generalized unitarity is based on a couple of generic observations which apply to all local quantum field theories, or rather they don't need to be quantum, or local field theories. So observation number one is that integrands of amplitudes are all rational functions. And as such, it should be possible to determine them from their poles and their residues. The possible poles, they turn out to be fixed by the number of external legs of the amplitudes and the loop order one cares about. And they are organized in terms of graphs. And these graphs, you may think of them as essentially the same graphs as in Feynman graphs, except that they don't carry the same mathematical expressions. The corresponding residues, they are fixed by locality in general words, or more specifically by multi-particle factorization. So here are a couple of examples at tree level. So this is a generic tree level of 4-point amplitude. If we want to see a pole in here, we need to adjust external momentum. Let's assume that we take the Mandelstam variable S to be small. Then that will fish out the pole corresponding to 1 over S. The corresponding graphs looks like this. And the residue is very much a sum over all the possible 3-point amplitudes that one sticks in, that one can attach to these 3-point vertices. So 2 external lines are the fields on the external lines are fixed. Therefore, the Lagrangian tells us what exactly can sit in here. So this is the pole, and then there is a finite part. One could, of course, look at T-channel pole, and then this is the T-channel pole, and there's another finite part. And this latter finite part has information about the former singular part, and the former finite part has information about the latter singular part. And if you know all of these, then it is possible to reconstruct, in most cases, the amplitude. Here is another example in a little bit less detail, a 6-particle amplitude. If we want to look at a 3-particle pole, pick, say, S1 to 3 to be small, then that fishes out the pole corresponding to that, and a 4-particle amplitude on each side of that pole, and then terms that are finite. So locality of the underlying theory and also unitarity of that theory imply that these poles are simple. Of course, if one assumes that the original Lagrangian has, I don't know, a 4-derivative quadratic term, then these poles won't be simple anymore, but that theory also won't be unitary. And then, as I said, the residues are given by lower order amplitudes. I should have said in the beginning, please feel free to interrupt with any questions you might have. So let me pause for a second here and ask if there are any questions on this. All right. If there are none, let's proceed to loop level, where the story basically repeats. If you the story basically repeats, except that now one has to actively reach inside these loop amplitude to set to fish out poles, because one cannot adjust anymore just external lines to set more than one particle on shell. So for a 6-point amplitude, here is at one loop, here is a set of poles that may appear. There are four propagators that could potentially be set to 0 or 3 or 2. And as an example of residue corresponding to this amplitude, to this pole, it would be the 3-level amplitude sitting in this corner, and then another 3 amplitude sitting in that corner, and then another one sitting in that corner, and last another one here. And of course, this is summed over all the possible intermediate states. For example, in a gauge theory, this would be the sum over all possible gluon polarizations, or in a gravity theory, this would be the sum over all the physical graviton polarizations in here. Same happens at 2 loops. And here is another example. And of course, it proceeds to any loop order. Now, having said this, an amplitude is in general determined by a so-called spanning set of cuts. That is, a set of cuts, I should say these residues are referred to as cuts. So a spanning set of cuts is a set of cuts that contains information about all the poles that may appear in the amplitude. And the ones that I drew here at 2 loops and at 3 loops, they are a spanning set of cuts, as it turns out. When we are going to specify to specialize to a classical limit, we are not going to use these cuts because these are a little bit too general. Indeed, restriction to classical limit and especially to the potential region will restrict these set of cuts and make them substantially simpler than the ones that I drew here. Okay, so this said, generalized unitarity, to basically dot the i's and give credit where credit is due, is the reconstruction of amplitudes integrands from their poles and residues. And the residues are sums of products of 3-level amplitudes. This can be interpreted as a reorganization of Feynman diagrammatics, and that reorganization manifests and enforces gauge invariance at every step. Therefore, one does not have unphysical states at any stage. And as I was saying, the classical limit can be, and in classical calculations, it is enforced at least part, it is enforced at this stage. It will be also enforced later on, but the starting point is here. One draws only the cuts that, one evaluates only the cuts that are relevant. So how do we compute the cuts? One, of course, has various options, but the one that we use is to construct the matter gravity amplitudes from matter glue amplitudes via the double copy. We could, in principle, use KLT relations instead, because these are 3-level amplitudes. However, the double copy is a lot more flexible here because it hands us the residues and in a form that's already attached to graphs. Therefore, it provides quite a bit of structure, which is useful to keeping track of these of where these what of the graphs these residues belong to. So here is the standard example for double copy, but here is how this translates into a graph structure for the cut. Imagine that one cares to compute this particular cut, which appears in the 4 p.m. potential calculation. So there are several 3-point amplitudes that each of which has a single graph, so it doesn't matter what one picks for it. But there are 2 4-point amplitudes. Like I said, one could in principle just use KLT relation, multiply all these trees and obtain a big mess. However, if one uses this double copy construction for 4-point amplitudes, one already knows that in here and in there is a sum of 3 graphs. So just expand all of these, and here are some examples of what you get. There are 3 here and 3 there, so you get 9 graphs. And each of the circled propagator represents one of the graphs buried in here. So by just using this this form of the 4-point amplitude, this cut is already organized in terms of graphs. And one can use all sorts of existing technology to worry about evaluating, say, integrals on cuts, or organize the merging of cuts, organize the identifying the residues, the common poles and residues between various cuts. So right. Another thing that we need to worry about is the sum over polarizations. That is the sum over physical states in here. It's this sum. Because we construct gravitons as products of gluons, we don't get them alone. We get them together with friends, like the dilaton and the axion, which need to be projected out. What we would like to do is to actually sum over just the graviton states, and this requires using superficially, it requires using a projector, which depends on a reference null vector R. Now, in this, it can be used. It's not terribly pleasant, but it can be used. However, it was pointed out that one can get rid of these reference vectors if the amplitudes that enter the cuts have a very special property. That is, they obey the word identities on any one leg without using transversality of any of the other remaining gravitons. If that's the case, then all the terms in here, all these k times r terms in the projector, physical state projector, drop out. And the sum over polarizations becomes just the normal de Donder gauge propagator, the numerator of the de Donder gauge propagator. So things basically collapse and simplify. Any questions about this? All right. Now, as I was saying, we want to enforce the classical limit as early as possible, and that is already at the level of drawing and evaluating the cuts. So for that, we of course use the classical the scaling with the momentum transfer that we want. And for that, it's useful to have 3-level amplitudes that have exactly the same Q scaling, that is momentum transfer scaling, that's as those of Feynman diagrams. That is a coupling of matter with graviton scales like Q to the 0, and 3 graviton vertex scales like Q square. That's just because there are 2 graviton momenta in here. And the same for 4-point gravitons and so on. So with this scaling, one just looks at cuts and discards everything that does not have this scaling at L loops. And that's for scalar scattering. If one has scattering of particles with spin, then things become a little bit more intricate and more care is needed. But if we restrict for the sake of the discussion here to scalar scattering, anything that doesn't scale like this can be discarded. There's of course a log when L equals to 2. Right, so this is the first step where we discard things. The second step where we discard things are we discard diagrams or contributions to diagrams that are at least intuitively quantum. One can also argue more precisely that they are quantum. For example, a graviton self-energy. Another kind of possible contributions that we discard are those that do not lead to long-distance interactions, such as diagrams that that contain a four-matter interaction in which the two massive particles that scatter interact at one point. So any cut that might contribute to something like this is discarded. Then last but not least, if we care about just potential construction of a potential, then one can also discard diagrams that or cuts that do not contribute, that at least intuitively do not contribute to potentials, because, for example, they cannot be realized by instantaneous interactions. For example, when there is no way to have an instantaneous interaction between this point and this point, while in the middle of it emitting a collection of other gravitons. So this cannot contribute to a potential. And for exactly the same reason, and for reasons that will be explained probably in Mao's talk tomorrow, any contribution that does not have at least one matter line in each loop can also be discarded. And this has to do exactly with the integration, with the evaluation of integrals. So putting all this together, here is an example of simplification of cuts. So I was mentioning before that this is a spanning set of cuts for two-loop amplitudes at 4 points. The cuts that we actually use are these ones. They have quite a few more lines that are cut. So here are 5, here are also 5, and here are 6. Whereas here one has only 3 and 4 matter lines that are cut. That is, one looks only at triple or quadruple poles. So this, of course, simplifies lots of evaluations quite a bit. Now, let's assume for a second that somebody hands you all the cuts. Now, how do you reconstruct the amplitude, or rather the integrand? Well, there are quite a number of options, and perhaps the most naive one is that just freestyle it. You look at the cuts, you kind of arrange them a little bit, and then you just see by eye what's the integrand, what's the function that has those poles and residues, and that's the answer. And of course, this works very well at one loop, perhaps at 2 loops, but it gets unwieldy pretty quickly. So there's another option which is somewhat more systematic. One starts with an ansatz in terms of all the possible poles that appear, and each of these poles has some ansatz numerator, and then one just looks at all the poles, all the residues, one matches with the poles and residues constructed as described before, and then one solves a large linear system, and that determines the ansatz numerators. This version has been extensively used in various high loop calculations in, for example, in n equals 4 super-Yang mills through 4 loops. Now, something that's quite a bit more systematic, and it makes things look quite a bit more bite-sized, is something known as matching as IBP matching, or matching of an ansatz based on master integrals. This improves on the previous on this kind of matching, in the sense that here one has a complete basis of rational functions, but does not have but has an overcomplete basis of integrals. Here one has a complete basis of integrals, and therefore one discards lots of total derivatives from the previous ansatz. So to carry out this this procedure, one needs to know a priori what the master integrals are that can appear. That is an independent set of integrals given the number of external lines and the loop order. Then the ansatz looks like this. These coefficients Ci that are to be determined, they depend only on external kinematics, that is P1, P2, and masses. So to construct them, one just takes each cut, then reduces that to master integrals, and then compares that with the cuts of this ansatz, and then simply one reads the coefficients. A good thing is that there are consistency checks built in. If only
Massimo, sorry, Bianchi. So when you say, so this procedure already is applied to the reduced set of diagrams that can give a classical result, or you have to apply it before?
You can apply it at any time. We apply it after. We apply it to the diagrams that give classical results. If one cared about a full quantum mechanical calculation, of course, one should apply this in the beginning.
Yeah,
and
sure.
never say a word about classical limit. But we definitely apply this after restriction to the classical limit. Yes. Okay. There are several reasons to do this, which I will get to in a little bit. Basically, doing it in the beginning, without the classical limit is substantially more complicated.
Thanks.
Mm-hmm. Right. So the consistency checks I was mentioning is that each of these cuts each of these coefficients, well, not all of them, but most of them are determined by more than one cut. And of course, they have to be the same, regardless of where they are determined from. Therefore, if they don't come out the same, then, well, something went wrong and one has to revisit. So here is an example of how this works. And I'm going to do this as a one loop example, but it's only because the higher loop versions are somewhat more complicated, but they work in exactly the same way. So at one loop, it's been known for quite some time that an amplitude in 4 dimensions can be decomposed into scalar box integrals, scalar triangle integrals, scalar bubble integrals, and then bubbles on external lines and tadpoles in the case of massive particles. So let me ignore these for now because these are not classical, and focus on these guys. So now imagine that we have a field theory that contains derivative interactions. For example, imagine that we have a theory that describes spinning particles. Then naturally, an amplitude will have loop momenta in the numerator, and because there is a spin vector, there will be just loop momentum dotted into the spin vector. So here is an example of something like that. One can reduce this to this is the form of the reduction. It reduces to scalar integrals, scalar triangles, and another scalar triangle with different coefficients. Now, if one cares to do this, if one does this on the cut rather than on the full integral, then here is what happens. Right? Imagine that we cut these 2 lines. Right? That is, on the right-hand side, we also need to look at only pieces that contain these lines to be cut. Otherwise, we can't construct that cut. The only diagram here that has that cut is the former. Therefore, by taking this T-channel cut that contains an L mu in the numerator, one can determine the coefficient of completely determine the coefficient of this box, of the scalar box integral in this ansatz. One can, of course, repeat this for say, an S-channel cut, though in this case it's quite a bit less restrictive. One determines again here the coefficient of the same box integral. So this stuff better be the same. But one also determines here the coefficient of one triangle and also the other triangle. So this is how it works. Take 2 loop integrals with whatever numerator momenta one has, reduce them, and read off coefficients. So there are other methods that are related to this, but since I seem to be running out of time, let me not dwell on them. Again, this example was given at one loop. At higher loops, there are things, well, apart from having more complicated integrals, there is the little issue that we don't have a generic integral basis. However, on a case-by-case basis, this can be constructed, and there is work by Johansson, Kassauer, Larsen, and others that aim at constructing a more generic and algorithmic way to construct IBP basis. But again, on a case-by-case basis, one can always construct an integral basis and carry out this procedure. And last but not least, there is yet another method that goes by the name of the method of maximal cuts, which is just as algorithmic as the previous one. This one basically is iterative. One starts with the strongest pole there is. Here is an example, and takes the residue, cleans it up a bit, it extends it off shell, and then symmetrizes it if one wants to get a, excuse me, if one wants to get a result that exhibit graph symmetries, and this is iteration number 1 for the integrand. At the next pass, one looks for slightly weaker poles, that in this case a 3-particle pole, and compares the result of the actual cut calculation with the cut of this of the result of step 0, and then one constructs the difference, which is by definition local, and then one symmetrizes it again and constructs this object. Puts it take this, push it off shell, put it on top of the 3 of the poles, of the corresponding poles, and that's iteration number 2. And then repeat this until you run out of cuts, and the resulting integrand is just the sum of these guys. And the reason this is the integrand is that essentially by construction, this function here exhibits all the poles and of the amplitude, and also it has all the correct residues, because again they are by construction the correct ones. This is, if you wish, a pass number 1 to the construction of the integrand. And like I said, this can be done directly in the just on the cuts that contribute to the classical limit. Now it turns out that there are further terms that are non-classical that are still in there, because the cuts weed out lots of non-classical terms, but they don't weed out lots of some of them. So to weed out the remaining ones, it's useful to pick a specific choice of momenta that originates in the work of Sudakov, Beneke, and Smirnov, and in the context of our discussion was pioneered by Julio Para-Martinez, Michel Ruff, and Mao Zeng. So the idea is that instead of P1 and P2 as incoming momenta, one picks these P1 bar and P2 bar, which are P1 and P2 slightly shifted by the momentum transfer. And with this choice of with this parametrization of external momenta, it turns out that all the integrals can be expanded into. It turns out that these momenta are orthogonal on the momentum transfer, and therefore all the integrals now depend on exactly one parameter. That is the dot product of P1 bar and P2 bar. Anything else that might have appeared in other parametrizations like P1.q or P2.q is now buried in P1 bar and P2 bar, or it's buried in these mass parameters, which can be scaled away. So with this in hand, a generic integral can be expanded at small momentum transfer in this form. There is a sum over some k, which runs over integrals, but each of these integrals has a specific dependence on the mass, m1 and m2, and also a specific coefficient that depends on q. Take this, plug it into the integrand, and then throw away anything that doesn't have the right scaling, that hands you exactly the classical integrand, and that's the end of the story. The only thing that's left to be done is the evaluation of these integrals. So to stress again, Q dependence is manifest, and therefore one can actively remove all the quantum terms. The mass dependence is also manifest. And because of this, one can relate pieces of the classical integrand with the corresponding terms in the self-force expansion. So
yeah. It remains 15 minutes, including the discussion.
Okay, thank you. I should be done in about 5 or so.
Good.
Thank you. So now it is time to put everything together. There are a few options again. But I'm pretty sure you already know what they are. So for example, one can reconstruct the integrand based on the classical cuts using either an ansatz or the method of maximal cuts. One can expand it as just described and remove the remaining quantum terms and then integrate. That's option 1. Option B, or option 2, is you just at the level of cuts expand them as described here. And at that stage, remove all the quantum terms, and then take the result of this expansion and merge the expanding cuts via IBP merging, and then the result, and then integrate the result. Already at step 2, one can compare these two approaches, and perhaps not surprising, with the same choice of master integrals. They do agree. They should agree, and they do agree. In the approach of Kossover, maybe, and O'Connell, one can use exactly the same techniques to construct the various pieces of this formula, like whatever the loop amplitude enters here, one can construct it this way, and also the various pieces that appear here. And then one is again left to integrating the remaining integrals. And last but not least, everything that I said was Lorentz invariant. But one can, of course, expand at any stage one desires in velocity. Though if I were to make a recommendation, I would suggest doing the expansion after cut merging, because otherwise things might get a little bit confusing. So as an example, let me just flash the again the cuts that contribute to the order g to the 4th potential, and contrast them with the with a spanning set of cuts at 3 loops, which is this one. So there are, like I said, there are more cuts, but they are quite a bit simpler than these ones. And among the master integrals one gets, some of them look like these. There are quite a few more than these 4, but here's an example of some of them. So the way to read them is just look at the graph, put scalar propagators for the blue lines, put iconal type propagators for the green lines, that is matter momentum dotted into loop momentum for these. And then wherever you see one of these guys, that's a numerator factor in the master integral. Now, of course, not all master integrals need to come with non-zero coefficients, and some of them do come with zero coefficients and here is one of those that happens to come with zero coefficient. We don't have a specific explanation why this and its, I don't know, 40 or 50 other friends come with zero coefficients, but they certainly do. So upon integration, one finds the same expression that appeared in Zvi's talk. So as mentioned, the mass dependence described here by Nu is manifest, and it was manifest also before integration. The amplitude is organized in the form that manifests its relation to the radial action. These are the lower order components of the radial action, and one can of course read off the radial action at order g to the 4th from the first term. There's of course an infrared divergence because of the restriction to the potential region, and the expectation is of course that it will go away once at least conservative radiation is added, or the subpart of that would be the tail. Oh, I should also mention that again, because of restriction to the potential region, there is a fairly strong mass divergence in either at small masses or at large momenta, but that strong divergence happens to be consistent with dimensional analysis actually. And of course, with this thing in hand, one can construct the Hamiltonian to be used, if desired, for bound motion. And the new coefficient that appears is this one. Of course, in this specific form, it cannot be used because of the epsilon, but one can make guesses and for what happens when radiation effects are added. So this brings me to the end, and to the end of my time. So we did cover quite a bit of material here and a lot of technology. But the point is that particle physics methods are definitely useful and a useful way to think about problems in classical gravity. They are algorithmic and flexible. They build on gauge invariant building blocks. Integrands are determined by these building blocks, which are poles and residues. There are lots of methods one can choose from. And these methods apply equally well to spinless scattering, interaction of spinless bodies or interaction of spinning bodies in the presence of finite size effects, without those, in effective field theories, and they also apply in the case of outgoing gravitons. These methods have been tested both in particle physics as well as in the context they have been discussed here in for classical gravity calculations where they did push the state of the art. And there's always room for improvement, and we are always out keeping an eye out for sources of improvement. And an example of that would be an incorporation of the absence of iterations in a point particle effective theory of Kalin and Porto and Mogul, Plewka, and Steinhoff. Now, of course, since the talk was meant to be about higher order calculation, I cannot end without speculating what's possible. And of course, we believe that g to the 5th is in the cards, and even g to the 6th might be. The reason for the latter guess is that 5-loop calculations have been done in other contexts, so I see no particular reason why they should be inaccessible here, where there are substantially fewer cuts. However, progress hinges on integral evaluation, and for that, I would highly recommend Mao's talk tomorrow. And on that note, thank you very much.
Thank you very much for the nice talk, and we shall take questions. So I am looking to hands that are raised, so please raise your hands. Yes, I see one by Enrico Herman, please.
Hey Radu, thanks for this very nice talk. I have one question to your method B, or your B analysis chain, where you do first soft expansion, yeah, and then you do this cut merging at the master level. Mm-hmm. So how do you deal with the fact that once you do the soft expansion, often in cuts, super classical pieces cancel if you're not keeping track of the I epsilons of the propagators? So if you do that, do you secretly keep track of the I epsilons?
Mm-hmm. Yes and no. So the way we do this is that we never really put the full cut back together. We basically look at it diagram by diagram, and then in that form we fish out all the pieces, and we never really add things that literally don't belong together. we keep track of all the we keep track of all the graph structure. Let's put it out.
Okay, so you never hit it with together, basically.
That is absolutely correct. There is no such thing as together. If only because the thing would blow up, really, if you did that. But it's just too big.
Okay, we have another question by Rafael Porto.
Yes. Hi, Radu. Quick question. Why you guys didn't include the soft radiation? If this seems to be so straightforward, put this together.
Well, it's because we didn't want to at the time. We wanted the potential.
No, but you know the potential is ambiguous, right? At this order, you want to get the whole thing, right?
Mm-hmm. Yeah.
So what was the point to cut it off and not include the mushrooms and do the full soft region?
There was no particular point. This is what we decided to do.
Okay. Are we being recorded?
Yes, I think we are. Yes.
Okay. All right, we can discuss this later.
So the next question is by Donald O'Connell, please.
Thanks. Yeah, thanks, Radu. Yeah, can you go back to the bit, well, maybe near the start where you're talking about your different propagators? Yeah, these two-body or radio election type propagators.
Yeah, here they are.
Yeah, yeah. So the P.L, I guess that P becomes a Z direction later on, right? When you
that is correct. This was somewhat schematic. The actual thing is the way it appears is here. So in this form, the incoming momenta are taken along the Z direction. So this norm of P times Z is actually this P.
Yeah. Okay. Yeah. So I mean, compared to the previous propagator, you're picking the direction more sharply, like the L squared minus P squared.
No,
re-expanding a little.
As it turns out, this difference here contains terms of order Q and terms of order Q square, whereas this thing is manifestly order Q.
Yeah. So the order Q squared terms in the previous one are being re-expanded out, right?
That's right.
Yeah. That gets rid of the E1 and E2 stuff as well,
or?
Or are you just absorbing that into numerators?
It's probably absorbed in the numerator, just not written out here.
Yeah. Okay, thanks.
Okay, another question.
Perhaps I have one.
Okay, Gabriele.
Yeah, I was wondering how you actually deal with this so-called superleading terms. I mean, I guess you don't perform the actual integral and you recognize immediately that they simply correspond to iterations, and
that is correct.
Leaving nothing behind, nothing subleading behind. Is that so?
Yes, that is correct. It's let me try to keep this highlighted. So the last four terms, they correspond to iterations. And an intuitive way to find them is to look at the various master integrals that we get and look for those that have three two-particle cuts in the S channel, three two-particle cuts in the S channel, two two-particle cuts in the S channel, and one two-particle cut in the S channel. The one with three two-particle cuts corresponds to 3 times 3 times 3 times 3, and it's this one. And then the one with 2 is this one. And the other guys, the one with 1 is a combination of these two guys. But this can be seen at the level of the integrand. We don't need to evaluate these.
I mean, there is no danger that by keeping subleading terms in H bar for those superleading ones, you generate corrections which are classical. No, I mean, one is completely confident that they can just be neglected.
In theory, things like this would correspond to scheme dependence of the Hamiltonian rather and not of an observable. So of course we did compare what comes out of this kind of organization with what comes out of the organization in terms of the other poles. And, you know, physical results agree. Hamiltonians, well, also the Hamiltonians happen to agree in this case because we actually, in this form, we construct the Hamiltonian by starting from the observable and working backwards. But from this organization, it's the observables are straight out derivatives of these guys with respect to J. So.
Okay, thank you.
Okay. Thanks. In this slide, in the Hamiltonian, in the amplitude that you show, so there is this term with the pole, because there is still the conservative radiation part, yes, which is missing. But do you agree this is obvious that with the conservative radiation part, there will be also the pole which will cancel this one, and then the finite part?
Absolutely, yes.
Okay,
yes.
okay. Yeah. Which is crucial.
Yeah.
I have a question. On the first line, you show the amplitude, which is a nice gauge invariant quantity, and then from that you compute the Hamiltonian. And the Hamiltonian seems to be automatically in isotropic coordinates. And I wonder why, from the gauge invariant amplitude, then it is straightforwardly you compute the Hamiltonian in the particular isotropic system. Is there a reason for that?
The reason is that we wanted it in that gauge. So the way we constructed this Hamiltonian was to compute an angle out of this, that is just take I4 and d by dj of I4, and then match that with an angle computed from a Hamiltonian in the isotropic gauge. That's why it came out in the isotropic gauge.
Okay,
we wanted it that
construction.
Way. Yeah, that's right. It's by construction in that gauge.
Okay, very good. So I see no other questions, so we shall thank you again for the talk.
Thank you.
And our first